This video is for Math 1342 for Chapter 11. Chapter 11 is the shortest chapter we do, and there's only two sections in there we cover. Section 11.1 is called Goodness of Fit. And there's actually two different types of problems, but they're very similar to each other. Goodness of fit. In one of those situations, you try to see if all the categories are equally preferred. And in another version, you try to see if they match claimed percentages of some kind. And then in 11.2, we do what are called contingency tables or the test of independence. Test of independence. So if I have two sets of categories like, say, independence. Okay, just talking and writing at the same time. Test of independence. So you might have like gender on the side, male and female, and then the top might be a preference of something like Coke, Pepsi, or Sam's Club, something like that. So does gender, is it independent of the type of drink that somebody likes, or does it depend on the gender? Now, in a test of independence, there's going to be at least 2+ rows and 2+ columns of data given to you. In a goodness of fit, the way you can tell you have one of those is there's either one row or one column of given data. Now, sometimes there's what looks like a second one, but it's just the titles of it. So you can instantly tell, oh, is this from 11.1 or is this from 11.2 if you look at the way the data is presented to you. So the very first problem I'm going to do, I'm actually going to do number 2 first. There's only 5 problems here. 3 of these problems come from 11.1 and 2 of them come from 11.2. So there's the day at the top, Sunday, Monday, Tuesday, all the way to Saturday. So those are just titles of what this is about. There's really only one row of numbers here. How many people were born at some hospital on the different days of the week in some kind of sample? And do these births occur? The claim is that the births occur with equal frequency. So that day, it doesn't matter what day of the week, you can have equal number of births on any day. Or the alternative then would be they're not equal in some way. So typically for the null, instead of doing like mu equals 10 or P1 equals P2, instead of having symbols and numbers, they usually describe it in a sentence, which is why this box is so big here. So births occur with all different frequencies, at least 2 days are different. Births occur with the same frequency. So that's the nulls, that births occur with the same frequency. In other words, it's all equal. No matter what day you pick, I should see roughly equal amounts of births. And in a sample, they might not all be exactly equal. That's fine. But is this significant evidence that they're all roughly equal or they're not so equal? And then usually the alternative is at least one of them is different. We don't care which one it is. Here it looks like the weekends are a little lower than the other numbers, but maybe it's just a little lower. Maybe it's not significantly lower. But at least one day, at least one, it could be all of them, but it's not that they're all automatically different from each other. I'm not trying to show that every single day has a totally different number of births than every other day. That might be the case, but I'm not trying to show that. I just want to show there's at least one day that's different so that I can say they're not all equal. So typically you just write these in a sentence. If you were like taking an in-person class and taking a test on paper, you would just write these sentences out. But here in the computerized work that we do, then you just pick it out of the multiple choices there, basically. Okay, then we're going to calculate chi-square. So the way you do this over here, I need to put the original data in the first list. So Sunday had 43 births. Monday was 55. Tuesday was 61. Wednesday was 60. Thursdays, whoops, let me delete that, 62. Friday's 56 and Saturday's 43. So you usually can't definitively tell just by looking at the numbers. But you can sometimes get an idea, yeah, that seems like the weekend is a little lower than the rest of them. Maybe that's a significant difference, or maybe not. Okay, so then what we need is we need the average of all those numbers. In any problem where you're trying to say all the categories are equal, then the average is used for the comparison. So you can either take all the original numbers, add them up, and divide by 7, or there's a quick way to do it. And here, if I go second mode to quit the screen, second stat, and right arrow to the math column at the far right, and there's one that says mean. The third one down says mean. Choose that, and then tell it second and the number 1, because that's where the date is. So I'm doing the mean of L1, and this will tell me what the average number of births is for the whole week for this sample. So 54.28571429. Now, if you round it a little, then unfortunately it can be off a little bit. So let me multiply this by 7 to see what the total was. So apparently the total, if I would have added all 7 numbers, it would have been 380. There were 300 in total, 80 births over the whole week, and there's 7 days in a week, so divide by 7. That's how you're getting 54.28571429. Because I don't want to type 54.28571429 every single time, I'm going to type 380 divided by 7 just to make it easier to type. Now, sometimes you get a case where, more often than not, actually, the mean comes out nicer, like 54 exactly, or maybe like 54.5. So if it's a nicer answer, I would just type them all into L2. But here I'm going to do 380 divided by 7 just to get this as exact as possible. And if you go back up there, you can see at the bottom, it's 54.28571428. So that way there's no rounding issues going on. So you put the average in L2 as many times as there is a number in L1. So I have to put this in 7 times. And that's why I didn't want to have to type the long decimal 7 different times. So I'm just going to type 380 divided by 7 different times. Unfortunately, there's no copy and paste feature to just put the other ones in, but say the average had been 54 exactly, then it wouldn't have been too bad to just type 54 7 different times. But here it's not coming out nicely. But in one version of section 11.1, the goodness of fit, one version is where you hope that all the categories are equal to each other. That's the null. And then you just, whoops, I typed that one wrong. And then you just put the average in L2 as many times as there's numbers in L1. Okay, now this calculator that I'm using, this free one from this company called archive.org, this is about a 10-year-old calculator, which is why they're letting it be used for free. And if you go to Stat and Tests, and remember, if you up arrow, you get pretty quickly to the LinReg t-test. That's the one used for chapter 10. If you go up a little higher, there's one called chi-square test. Everybody that has an 83 or 84, any version of 83 or 84, any year that it was made, will have a chi-square test. That's only used for section 11.2, however. Newer calculators, like those ones where I have to explain if you're a paster, do this. Some of the newer calculators have one right below this that says chi-square GOF test. So you may have that because I'm guessing your calculator is probably not 10 years old. So if you have the chi-square GOF test built into the calculator, you'll see chi-square test, and then literally right below it, it says chi-square GOF test. That's GOF is goodness of fit, which is what section 11.1 uses. If you have that one, then you're going to be able to get the critical value and the test statistic and the p-value more easily. So then click that option for the GOF test. And I'm going off memory here based on what I've seen students in class have these. I think the only thing you have to change is the degrees of freedom, possibly. So it should say observed And it should have a L1 there already. Then there's expected. And then the default for that's L2. And then it asks for the degrees of freedom. So as long as you put your data in L1 every time, your observed data, the original data is called the observed data because we observed this in a sample. And then put the expecteds in L2, which is just simply the average of all the observed numbers. Put it in L2 as many times as there's numbers in L1. And then you just might have to change your degrees of freedom from problem to problem. And we had 7 different days of the week, so you probably would guess if somebody asked you how many degrees of freedom you think it is. With 7 days of the week, we put 6 degrees of freedom. So that's very similar to chapters 8 and 9 where you're doing degrees of freedom. It's just the number of categories minus 1. And then you can hit calculate below that. And when you hit calculate, you'll see the very first long number is the chi-square test statistic that they're asking for right now. And that could be used if you wanted to do the critical value method too. And then right below that's the p-value. My calculator doesn't have a GOF test because it's old. And I'm sure I always get a few students that take this class that still have the older version too, because maybe it was a hand-me-down from older siblings, or they just had this one for a while since they were back in high school. So in case you don't have the GOF test, then here's what you can do to still get these answers. And if you have the GOF test, don't do what I'm about to do. But there's a formula for the test statistic that goes, this is only if you have to do it by hand. Chi-square is the sum of the observed minus the expected squared divided by the expected. And I've got the observed in L1. I got the expecteds in L2. So by the formula, if you just follow order of operations, you would do the parentheses first. So in L3, I need to do observed minus expected, which is L1 minus L2. So L3, turns out if you don't have the GOF test, you just always do L1 minus L2 in L3. And you basically wouldn't have to memorize it. You could just write the steps down. So go into L3. Go to the top of L3, not the first entry, the top, and tell it L1 minus L2. And it does all the subtractions for you. Then you go to L4. The next thing in order of operations is exponents. So now I'm going to do what I just put in L3, and I'm going to square it. So in L4, you can do L3 squared. Go to the top of L4, L3 squared, press enter, and it does them all for you. Finally, one last thing. And another thing that's nice is you keep taking the last thing you did and do one more thing to it. So now take the L4 answers that you got, and you're going to divide by L2, because the top of this fraction is L4 and the E in the bottom is expected. That's an L2. So L4 divided by L2 is what we always do in L5. The sum of L5 is the test statistic. So I can get that if I do second mode to quit the screen, second stat, go over to math. In addition to doing means, you can do sums. Right there, number 5, sum. If I ask it, what's the sum of all the numbers in L5, that would take a while to do that all by hand. But anybody that had the chi-square GOF test, your first number that should have appeared on the screen would have been 7.284210526. That's the test statistic, the chi-square test statistic. And they'll ask you to round it to, in this case, 3 decimals. See chi-square equals. So it was 3 decimals would be 7.284. 7.284. Okay, then for the p-value, so what I want to do is I'm going to do second vars, and you guys might remember normal CDF and inverse norm. Well, this is a chi-square CDF. Chi-square CDF, because this whole section's about chi-square. And for chi-square CDF, if I go between 0 and this test statistic that I just got, 7.284, 284, and I'm going to probably type the whole thing here just to be safe. 10526. And then it also requires you put the degrees of freedom at the end, so that would be 6. If you do this, you're getting the area between the beginning of a chi-square graph and where your test statistic was. Well, p-values are all about the outside of that. So what's the probability I go way out into the tail region? So then you can 1 minus this answer to get how much there is in the tail region. 295 maybe, or 2954. I don't know how many decimals they want. 4 decimals. 2954. So this way it's possible to get the test statistic and the p-value even if you don't have the GOF function like a lot of newer calculators have. The good news is probably 80% of you watching this video have that already built into the calculator, and therefore you'll be able to get it much quicker than I just did. This took me maybe 3-4 minutes to do this, where you can do it in 15 or 20 seconds. So the rest you should know how to finish, because the rest is just like chapters 8 and 9. I just got a p-value of 2954. This is greater than any alpha they would give me, but I should check which one it was. Alpha was 0.01 significance level. Even if I add 2 zeros so that I'm still greater. So we do not reject the null. Do not reject the null. The null said that they're all equal, and even though the weekend seemed a little lower, it was only a little lower. That wasn't a significantly lower amount on the weekends. So do not reject the null, and that means there's not enough evidence. Or they like to say not sufficient evidence. And because the claim was in the null, then to reject the claim. I can't reject the claim. The claim said all births happen equally on different days, and I can't reject that. So fail to reject the null. There is insufficient evidence to warrant rejection of the claim. That's exactly like chapters 8 and 9 right there. So how might the apparent lower frequencies on Saturday and Sunday? See, there's slightly lower frequencies on Saturday and Sunday. They're slightly lower, but that's not a significantly lower amount to say that they're not at least close to the other ones. See how it says induced or cesarean section births are usually scheduled during the week when possible, because that's when they have the main doctors there. So maybe that's what could cause those to be a little lower, is they could be all equal if not for weekends, but because the doctors don't work 7 days a week, they're going to get 2 days off. So then they can, in most cases, unless it's an emergency, they can just push it back to a weekday or do it before the weekend comes. So that's definitely a possible explanation why. So, but it's not a guarantee that that's the truth, but at least we could have some reasonable explanation why we're seeing slightly lower numbers. But just because the numbers are slightly lower doesn't mean that you have evidence that the days are all different. So let me go back to 1. The reason I did number 2 first is, you know how 2 has these top categories listed for you: Sunday, Monday, Tuesday, Wednesday. And sometimes they use numbers instead. And then if somebody sees this, they think it's a problem from section 11 too, because they think they have 2 rows of numbers and 2 columns of numbers, or more than 2 columns. The top numbers are not anything. They could be Monday, Tuesday, Wednesday. They're just category names. In horse racing or dog racing, they put numbers on the horses or dogs. So that's just like putting Sunday or Monday on something. So the post position 1 through 10, I don't use that number. It's no different than a category name. It's often easier to name things by numbers sometimes. So this is still a goodness of fit problem. I only have 1 row of numbers. How many wins did each of these pole positions get? So in that regard, it's similar to how many births are there on a given day. So this is exactly the same type of problem, just different data and different numbers to work with. So when you're ready to start a new problem, you only have to clear out list 2 and list 1. You can leave the other ones still filled in. So list 1, I'm going to put the wins, not the pole position, just the wins. 20, 15, 12, 14, 14, 6, 7, 13, 4, and 11. And again, this seems kind of different. The lowest one's 4 and the highest one's 20. That's 5 times as much. So it doesn't seem very likely these are all equal. So let's get the average now. Do second mode to quit the screen, second stat, math, and the mean of list 1. Hopefully it comes out nicer. Dividing by 10 at least should make it nicer. See, it's exactly 11.6, and I don't have any rounding issues. So go into L2. Even if you have the GeoF test, everybody has to fill in L1 and L2. So you got to put 11.6 10 different times in L2. Oh, I already have a typo. Okay, there's all of them except I got to go back up to the typo. There, 16 was supposed to be 11 point. I guess I typed a double one too fast. There, okay. So if you have the GeoF test, go in there right now, do stat, test, and go up to the GeoF test if you have it. And then all you have to do is change the degrees of freedom. There's 10 post positions here, so it should be 9 degrees of freedom. Change the degrees of freedom to 9 and hit calculate, and you'll get the test statistic and the p-value all together. If you don't have the GeoF test, then you got to do like me, and luckily the steps are the same, so you'll maybe get used to this pretty quick. L3 is always L1 minus L2. L4 is always L3 squared. And L5 is always L4 divided by L2. And if I sum up L5, that's the test statistic. So second mode quits the screen. Second stat, go over to math and go down to the sum. Sum of L5, 17.793 is the test statistic. 17.793. Oh, I forgot to do this. Okay, so where's the claim? Should bettors consider the post position of a horse race? Oh, no, wait, here's the claim. Test the claim that the likelihood of winning is the same for each post position. So the null is always like that, there's nothing special going on. Everything's roughly equal. So wins occur with equal frequencies in all the different post positions. That's the null. The alternative is at least one post position is different than the others. Maybe they're all different, but at least one's different. There may be some advantage to one, like if you're in the one box, you have a shorter distance to run total, and you don't have as many horses. You have no horse on your left, so then you got a little more elbow room. So there's the test statistic, 17, I forgot what it was now, 17.793, 17.793. So when you do the p-value, if you want to hit the 1 minus right away, you can do that, or you can do it after you calculate it, but 1 minus, second vars, chi-square CDF. You always put 0 first because a chi-square always starts at 0, it never goes into the negatives. You always put whatever test statistic you got, and it's best to type the whole thing rather than just rounding it off. And then you got to put degrees of freedom last, so there will be 9 degrees of freedom here. So the p-value is 0.377. If you bump that 6 up to a 7, 0.377. 0.377. And this is good. I was hoping this would happen. The significance level is 0.05 this time. At least we're going to get the opposite answer of the previous version. See here the p-value was greater, so we did not reject the null. Now we got a p-value of 0.377, and this is less than alpha, which is 0.05. Although don't get tricked by 377 thinking that that's greater than 5, because this is really 500. 0377 is less than 0.0500, so reject the null. Reject the null says you can win equally in any pole position, but we're rejecting that, saying no. There is sufficient evidence. There is sufficient evidence to reject the claim since the claim's in the null. If the claim was in the alternate, we would say to support the claim, but now we're going to say to reject the claim. Reject the null, A or C. There is insufficient evidence. No, there is sufficient evidence. So C, reject the null. There is sufficient evidence to warrant rejection of the claim. Yes. Now, if you change alpha to 0.01, then you could get that to go the other way. But based on the results, should bettors consider postposition? Yes, they should, because this is saying some have an advantage over others. You wouldn't just blindly look only at the horses. Okay, so we did 2 examples of a regular chi-square test where we assume they're all equal to each other. There's another kind where we know they're not all equal, and we're not going to try to force that. Clearly, they're not all equal. If you buy like bags of Skittles or M&Ms, they don't make the colors equal. Some colors happen a lot more than others. Like I know in M&Ms, they make a lot of brown ones that match the color of chocolate, but they don't have as many, like blue ones are very rare. And if you go on the M&M website, they even tell you their percentages they claim to do. So that's the idea here, is some candy company says they make their color percentages the following: 14% red, 20% orange, 16 yellow, 8 brown, 26 blue, and 16 green. So clearly they're not all equal then. So we can't get away with saying that. But what we would say, apparently they're not even making me do the null and alternative here, but what we would say is that the null would be something like the candies occur in the percentages given or claimed or provided by the company or something like that. That, in other words, we believe what they say the percentages are. And then the alternative would be at least one percentage is not true. At least one, maybe more than one, but at least one is different than what they say it is. And then if we could get a sample that shows a significantly different percentages than what they say, then we would have evidence to reject the null. Okay, so here we took a sample of candies, and maybe we enjoyed sampling these candies because then we got to eat them when we were done counting them. There were 12 reds, 27 oranges, 8 yellows, 5 brown, 27 blue, and 21 green. The fact that these are different from each other, it isn't an instant, oh, we must be rejecting the null, because the percentages are different. So maybe brown doesn't happen that much. In fact, brown only happens 8% of the time, so that could be why it has a low number in the sample. So now it's really hard to tell just by looking at it, does it seem like they're green with the null or not. So there's just one difference compared to the first 2 problems. The only difference in this whole problem is how do you do the L2s? It turns out you don't just put the average in L2 as soon as there's percentages given to you. So I'm clearing out list 1 and list 2. I'm going to type the 6 colors of candies in list 1. So list 1 gets 12, 27, 8, 5, 27, and 21. The observed always go in L1. So L2, here's what you just got to do. Even if you have a fancier calculator, everybody's going to have to kind of do this by hand. So L1, I'm going to write the numbers down here. 12, 27, and 8. This is problem number 3. And then we're going to do the L2s over here. 5, 27, and 21. Instead of doing the average and putting the average down 6 times, here's what we do instead. Add up all the frequencies, and I'll do it with a simpler calculator so I can see it all at the same time. 12 plus 27 plus 8 plus 5 plus 27 plus 21. Okay, it's nice when this comes out to 100, but it could come out to anything. So whatever the total is, you have to take the total and multiply by the given percentages. and change them to decimals too. So let me make sure the order was the same. Red, orange, yellow, brown, blue, green. Yes, the order is the same. So the red is 14%. So if the total's 100, this turns out to be easy to do because then you just 100 times 0.14 takes me right back to 14. So it's going to seem like I'm putting just the percentages down, but it's only because I'm multiplying by 100. If the sample size was 120, then they would be different. The L2s would look different than what the percentages are. But instead, I'm going to do 100 times each percentage, and it's just going to turn it right back to the way it looked as a percentage. So 20% for orange, as a decimal, 20% is 0.20, but then when I multiply by 100, it goes right back to 20. So in essence, this will be easier. 16 and 8. And 26 and 16. It's not always this easy. It's only this easy when the sum is 100. But see how the red, we got 12 in a sample, but we would expect to see 14. We got 27 of this color when we were supposed to get 20. Here we only got 8 when we were supposed to get 16, so that's only half. So as each one of these differs a little or a lot, that one was really close right there. And so one of them seems to be off quite a bit. The rest are somewhat close. Some are really close. Some are off a little. The more they're off, the more likely you are to reject the null. So put those 6 numbers in L2, 14 and 20. 16 and 8. 26 and 16. See how you're just not putting the same number in there 6 different times. Everything else is the same. So if you have a GOF test, run it right now and just put 5 degrees of freedom because there were 6 candies. The rest of us that don't have that in our calculator, we have to do it the long way. L1 minus L2 in L3. Then go to L4 and tell it L3 squared. Then go to L5 and tell it L4 divided by L2. At least all these steps are the same as the first 2 problems. The sum of L5 is a test statistic. So second mode to quit, second stat, math, sum of L5. 9.462 if you bump this 1 up to a 2 because of the 6 after it. 9.462. 9.462. They didn't even bother to do the null and alternative. They just went right to the test statistic. Oops, okay. Oh, it says 2 decimals, duh. They do that sometimes where they, see if you're paying attention, I guess. The last 2 wanted 3 and this one wanted 2. Okay, so they tricked me there, but hopefully you won't get caught by that. And then the critical value, oh, they want the critical value this time, okay. I was about to do the p-value. Okay, critical value, so I have 5 degrees of freedom because there's 6 candies, and there's a 1% level of significance. So there's a chi-square distribution table right here. And if I find 1%, 1%'s right there, and go down to 5 degrees of freedom. 1, 2, 3, 4, 5, right there. 15.086. That's the 1% level of significance with 5 degrees of freedom. 15.086. So they're doing this by the critical value method rather than the p-value. Now I could do the p-value still. If I do 1 minus second vars, chi-square CDF, 0 always is first, and then you can even do this and hit second answer to grab that whole 9.6 number, comma, 5 degrees of freedom. The p-value is 0.920. You could do the conclusion with the p-value if you wanted to. 0.920. So the p-value method, you do 0.920 and compare that to the 0.01 alpha. It's greater, so do not reject the null. There's not enough evidence. There's not sufficient evidence to support or reject the claim. I didn't check where the claim was. But the critical value method, what happens is you're in a chi-square graph that never goes into the negatives. It starts at 0 and it's skewed to the right. And then my test statistic was 9.46. So if you get, the 9.46 is the test statistic. And the critical value was 15.086. 15.086. In the critical value method, you have to land in the tail that you care about to reject. They call this the rejection region. I would need to get a chi-square test statistic larger than 15.086 in order to reject. And 9.4 is not. 9.4 is still back here in the main body. So I don't have an unusual result. I don't have anything significant going on here. Both methods are telling me the exact same thing. And really, if you do both methods in the same problem, they should tell you the same thing. The p-value method and the critical value method are saying I don't have a very unusual sample here. So there's nothing to say that anything's wrong with the null, which is always assumed to be true. Do not reject the null. Do not reject the null. There is not sufficient evidence to warrant rejection of the claim. And the only difference on 3 versus 1 and 2 was the L2 was not simply the average. It was the total times each percentage. And if the total's ever 100, then it's easy to do that. But if the total wasn't 100, then we would do that a little slower. Okay, so let me give you the magic word of chapter 11. This will be the last time you need a magic word. I'm going to make some videos for the review for the final, but they're not going to have any magic words. So that portion of your grade of video watching ends right here. And if you know what the last two were for chapter 9 and 10, this should be part of that theme. Let's go with Planet Neptune. Planet Neptune is chapter 11. Okay, we have two last problems, and these are similar to each other. This is where the original data that you get from a sample, look at this here, I had to pull it up. There's two categories on the side, and there's two on the top, and it creates a table of numbers that makes what's called a matrix, where you have at least 2 rows and at least 2 columns. So some people call this the test of independence. So the null is always that whatever the first topic is independent of the second topic. And then the alternate is that it's not independent, or you could say it's dependent. So the null and alternative is definitely A. We always put independent in the null and either not independent or dependent in the alternate. You would never put not independent in the null, and we don't say accurate or inaccurate either, so it's definitely A. The good news is to get the chi-square test statistic, everybody can do this the same way. So even if your calculator is as old as mine, you can still do this one the easier way. So to do this, we're not going to fill in list 1 and list 2. What we go to is press second, and there's a button that has an x to the negative 1 on it. It's right next to the sign button, or right above the x squared button. By hitting second first and then the x to the negative 1 key, notice in yellow above that it says matrix. So this little table is called a matrix. When you have 2 or more rows and 2 or more columns of numbers, that's a matrix. In the previous section, we just basically had 1 row or 1 column of numbers. You could put a matrix on that, but it turns out you can't do that in this calculator with that. But once you get into the matrix screen, right arrow twice over to edit. I need to edit matrix A. I'm going to put the observed or the sample data in matrix A every time. So press enter to go into matrix A under the edit. You have to understand the size of a matrix in order to fill this in, but this is an easy one because even if you did it backwards, you'd get this right. But the size of a matrix is how many rows do you have? I have 2 rows, and then how many columns? I have 2 columns. This is a 2 by 2 matrix. So you just type, it's defaults to 1 by 1 the first time you come in here, so just type 2, enter, 2, enter, and it changes it so it looks like the problem on the screen. There's 4 zeros here waiting for me to type numbers in. So just type all 4 of these numbers in exactly in the same order. Put the 17 first, then the 47, then the 26, and then the 9. 17, enter. 47, enter, and it wraps you around to the next number that you need. 26 and 9. 26, enter, and 9, enter. You fill in matrix A. Turns out you don't have to fill in matrix B. Now watch, if I go to second matrix right now, see how matrix A is now a 2 by 2, but matrix B is blank. So it turns out when you do the section 11 ones, you have to do the expecteds in L2 or it won't work. But turns out here, this is kind of nice. You don't have to do the expecteds in B in matrix B. It actually does it for you. So go to Stat, Tests, and up arrow to the chi-square test, not the GOF one. The GOF is not used for matrix problems. Use the one that's just called chi-square test. If you have both of them, you got to be careful which one are you doing at which time. But for those of us that just have this one, we can't do it wrong at least. Go to chi-square test. This is very easy to do. There's nothing to do here. Observed is matrix A, and you do have to fill that in first. But see how it says expected in B? Turns out you don't have to do it. If you just calculate it, it does it for you. Now, if you try that with the GOF test, it'll be an error if you don't fill L2 in, but I don't know why the chi-square test works without doing the expecteds, and why does the GOF test not work unless you fill the expecteds in. It's kind of strange, but go down and hit calculate. It doesn't even make me do the degrees of freedom either. And there's your chi-square, and there's your p-value. So the chi-square test statistic is 20 point. I got to see how many decimals they want because they tricked me last time. They're back to 3 decimals now. 20.974. 20.974. Watch out for this p-value here because remember, p-value stands for probability. Probability can't be bigger than 1. You might get tricked and think the answer is 4.6, but probability can't be 4.6. It's actually 4.6 E negative 6 way at the end. There's an E negative 6. 4.6 E negative 6 literally means 0.0000046. You're moving the decimal 6 places to the left. And then if I round to 4 decimals, it literally rounds to 0, even though it's not technically exactly 0, but it's extremely close to 0, actually. The p-value rounded to 4 places is 0.000. It's nowhere close to 4.6. That always tricks people when they take tests. They don't even look at the end where the E negative number is. This p-value is less than any alpha they would give me. There's nothing smaller than 0. So no matter what alpha I get, it can be as low as 0.01, can be as high as 0.10. I'm going to be less anything in between. So reject the null for sure. I didn't even look what the alpha was because it's definitely less. Reject the null, and there is sufficient evidence to either reject the claim or support the claim, depending on how it's worded. So they're not even making me say reject the null. There is sufficient evidence. Do the results suggest that polygraphs are effective in distinguishing between truth and lies? So if they were not effective, then the null would be true, that it's independent. You can tell a lie and they can't tell. If you reject the null and agree with the alternate and they're not independent, then that means you're more able to tell who's lying and who isn't. So there is sufficient evidence to warrant rejection of the claim. Okay, that the subject is independent of the polygraph test indication. I think it's C, because that 95 is just for the cutoff. It's not really exactly 95. So yeah, there is sufficient evidence to warrant rejection of the claim because I rejected the null. Okay, same, and there isn't 2 different versions of this problem. So if you know how to do 4, you basically could do 5 as well. The one difference here is, notice the matrix is not a 2 by 2. So if you don't know, is this 2 by 4 or is this 4 by 2, that could mess you up when you're putting it in the calculator. But there's 2 rows, male and female. There's 4 columns, blue, brown, green, and hazel. So apparently it's like eye color and gender. Does eye color and gender, is that independent? And you can have any of these colors of eyes independently of your gender? Or does gender somehow play a role in what colors of eyes come up more often? So the null is definitely that the eye color and the gender are independent. Gender and eye color are independent. And then the alternate is that they're dependent or not independent. So this is definitely D. Okay, let's run the matrix now. So one good news, if you go to the matrix, second and x to the negative 1 button, see how B's been magically turned into a 2 by 2? I never touched that. I discovered that at one point that I thought you had to fill them in like the other section. Turns out you don't have to. So go to edit. You only have to edit A every time you do a new problem. If you do the size wrong, it should look weird compared to the problem. My problem is longer sideways. If you do it the wrong way, it'll be longer up and down. This is actually, if you do a 4 enter, 2 enter by accident, see how it's longer up and down? The screen wasn't like that. So that, oh wait, I got to go back and up arrow back up here and do it the other way. 2 enter, 4 enter. That's a 2 by 4. And now it's longer sideways, just like it is on the screen. It should look exactly like this right here on the screen. So first you type the 355. Then it moves to the next number when you press enter. 300. Then 117. 162. Once I hit 162, watch when I press enter, watch the cursor. It's going to wrap around to the start of row 2. Boom, right there. Now I'm at the bottom left at row 2. So that's 378. 349. 198. And 199. Now, if you ever get an answer that's wrong and you can't figure out for the life of you why, I think what happens is sometimes students type 199 and they don't press the enter button. See how you see the 199 at the bottom, but up in the matrix it still has a 0 there. It hasn't registered yet. So I think students do that sometimes. So press enter now. Now the 199 is in there. So notice you don't have to do this, but if I go back to second matrix right now, notice that A has been changed to a 2 by 4. But B is still a 2 by 2. B still has the old problem. It's okay. I used to think you had to fill that one in too, but it turns out you don't. Stat, test, chi-square test. Even though B is the wrong one, if you go down and hit calculate, not only does it do it correctly, but look, if I go into second matrix now, look how B's been magically changed to a 2 by 4 and I never touched it. So that's the good news is in section 11.2, you don't have to do the expected, it does it for you. So the chi-square test statistic is 11.5996, however far they want it rounded. The p-value, I always look at p-value. Look at the very end and see if there's an e negative over here. There isn't. So then you're going to write it down like it looks, 00888 or 0089 maybe. So how many decimals do they want? They only want 2, so that could have tricked me because they asked for 3 a lot. So this would be 11.60 for 2 decimals. The test statistic is 11.60 if you wanted to use the critical value method. Or if it lets you do the p-value method, which is easier with technology, then you would say 0089 to 4 decimals. Oh, they only want 3. Okay. 009. Always read that because they can count it wrong if you're not paying attention to that. It already tricked me once. So use a 1% level of significance. And I got a p-value of 009 to 3 decimals. The given alpha is 0.01, and you might think 9 is bigger than 1, but this is actually 9 compared to 10 if I make them both 3 decimals long. And 9's a little bit less than 10, so reject the null. The null says that the gender and the eye color are independent. I'm rejecting that and saying, no, it is dependent. Depending on your gender, you're more or less likely to get a certain eye color, apparently, at least based on this sample. Reject the null, definitely A or B. There is sufficient evidence to warrant rejection of the claim that gender and eye color are independent. Okay, so this video was maybe the shortest one of the whole semester, but we only did 5 problems, and I got all 5 out of 5 correct, 100%. So we're all done doing homework now. And then there's a review for the tests that's similar to all the homeworks. I don't make videos for those, but because it's been a while on the earlier chapters and because the review for the final covers every chapter and the final is pretty close to the review for the final, so you should be able to do the review for test 4 on your own. Is just like the chapter 9, 10, 11 homework. There's nothing in there that's not in the homework somewhere. But I'll be making at least 2 videos for the review for the final. I'll planning to do half and half if they don't go too long. There are 35 problems in this review because there's like roughly 3 from every chapter. 3 or 4 problems from every chapter is what's here. So if I try to do this in one video, it might be 2.5 hours long. So I'm planning to do it in 2 videos, and unless maybe it might take 3, but I'm going to break this up into 2 or 3 videos so that they're each around an hour, a little more than an hour each. And then when we get close to the final exam time, I'll send these videos out, and then you can use that or not. Maybe you remember all the homework from the past. There's nothing in this review for the final that wasn't in the homework somewhere, but just in case you want to get, oh yeah, I forgot all about chapter 2, chapter 3, I don't remember anything about that, then you could use the videos to just help you do well in the final. But there won't be any magic words in the reviews for the final. So this is the end of chapter 11 video, and this is the end of looking for magic words of the chapter.